Okay, so let me, so I just stated the theorem that we proved last time, but there are some missing pieces. So let me recap the proof of where we were. So last time we, so let me first denote by the side. So last time we showed that on the one hand, we have that the following integral to be the grad of minus omega x for any g that so we saw this equality last time. Of course, assuming that this the characteristic function is a station the rotating percentage. Here, the end is the Newtonian sign like this. But on the other hand, we chose a specific vector b to be x plus gradient p, where p is a solution to the following elliptic equation. The conclusion is equal to -2 in the domain and vanishes on the boundary. So we plug this specific b into this the left-hand side in the integral. Then we found the following. We have, so let me call this I is equal to x times gradient x. Right. So I is equal to integral and we involve with n minus omega squared x plus gradient p times gradient so we made 4 claims last time. First claim is that we claim that A is exactly equal to B squared over 4 pi. And claim 2 was that V, the second moment of the given patch B is always bigger than or equal to B squared over 2 pi. And 3. That's the term C, the integral containing the gradient of P is equal to 1 minus 2 omega times the integral of P. And plane 4, so that the integral of PdS is always less than or equal to the squared over 4 pi. And here, also plane 2 and 4, equality is achieved if and only so once we have these 4 planes, then we can show that the I can be 0 only if the patches are this. So we already have I is 0, so that gives that.
Estaba apagado. La cosa más dura.
So since everything is okay, so actually I was going through these 4 clients today, but I don't know if I can make it today. But at least I will do like the first 3, and then let's see if I can do the last one. So let's prove the claims. So, for this part, so let's rewrite the equation, the integral as the x times the convolution is going to be y x the grid function y n of x minus 1 yes. So I just expanded this convolution as an integral. That is going to be integrating b. So we have x times, no, we have a gradient. So we have a gradient. And then recall that the Newtonian potential is just 1 over 2 pi times log. So we have 1 over 2 pi times the gradient of log x is just x squared. So like here, here the gradient of n is just 1 over 2 pi x over squared. So we plug in x minus y instead of x, so we get x minus y over x minus y squared and dy dx. So and then I'm gonna take only half of this quantity. The half of this quantity is going to be 1 over 4 pi instead of 2 pi. So we have x times x minus 1 over x minus 1 squared dx dy. Plus, we have another half. So I'm going to just copy the exactly same thing. And we integrate d x minus 1 over x minus y squared dx dy. But there's nothing I did. I just split it as 1 over 2 pi into 1 over 4 pi plus 1 over 4 pi. But here we integrate with respect to x and y variables. So we can just interchange the notation. That is going to be y and y minus x. And this doesn't change because we take the magnitude. Now we can put the integrand in one single integral. So we can write it as x minus y dot product with x minus y over x minus y dx. I just pull out the common factor x minus over x minus y squared. So I pull out the same factor from here, so we get a negative sign, and then the integrand is exactly 1. So we have one dx 1, which is just the square. So that exactly gives us the point 1. Then let's see the plane 2. So what is B? B is the second moment. B is going to be the x squared dx. But we can, if you have a patch which is assumed to be not a disk, then we can draw a disk that has the same area. We're going to just generate the shape. If you have this is the singularity is in there. This is the patch D. And then we draw. Sorry, I think I'm missing. So let's suppose the patch is like this. This is patch B, and we draw a circle whose area is the same, and then we split this integral into first we integrate from on the disk, and then we have to add this part, right? That is going to be b minus b squared over dx. So we have to subtract this portion here, which is going to be b subtracts d x squared dx. So here, B is a disk. Centered at the origin. And then you can just compute this one just using the polar coordinate, and you get exactly the square root of 2 pi. Let me just skip this part. And then we have these two terms. There's nothing I did. I just replaced the first term by the square root of 2 pi, and then we have the terms in here, and this is always bigger than or equal to 0, right? Because the area is the same, but we have a weight x squared, and that is always bigger than, if you like pick a point here, and then the distance is always bigger than any point inside the hole. So this term is always bigger than or equal to 0, and this term becomes 0 only when the patch is of this central origin. So that proves the second plane. And then just let me do the third plane. The third plane is not this plane, it's one step integration by parts. We have the gradient T times term C. Here, the gradient of the convolution minus omega x dx. And then you can do the integration by parts. So we are going to move this gradient to this term, but we call that P is 0 on the boundary. So there's no boundary integral, but we have negative of P times Laplacian of the same function minus omega. There was. I'm sorry, I think I made a mistake. Because we are taking the gradient, the quantity here shouldn't be a vector; it should be a scalar value function. Sorry, there was my mistake. There was a typo. So this is not omega times x, but omega over 2 times x squared. So we have this correction in here. So we have like this, and then we have negative of the Laplacian of something convolved with the Newtonian potential. It just gives you the same function because the Newtonian potential is the fundamental solution to the Laplace equation. So we have one of the characteristic function, and then you can just compute the Laplacian of x squared. That gives you 4. So we multiply 4 by the omega over 2, which gives you 2 omega. And then we integrate this on D, so this is just 1. So we get negative 1. I think there was another type. I think this was not this, but there should be a negative sign. So we get the, sorry, there was a typo. There should be a negative sign, but I think I forgot. So this proves the third plane. And I think we have to finish now. So I will postpone the last plane to Wednesday. Right, Javi, so we have to finish now, no? We have 20 more minutes, right?
Plane 4 is plane 4.
Yes.
Is what's called the subdynamic inequality.
Yes, thank you very much. Yeah, actually, I was told that like this can be written in a general way. It was proved in other earlier literature. Yes, so but we are going to use some variation of this inequality for the non-simply connected case. So in order for that purpose, I'm going to make a little bit more general statements, and then we're going to prove this. But I don't think we can finish the proof in 10 minutes. So I think we better finish.
One thing what you want to stop here.
I think I will do it on next day. Okay, thank you.